All right, hopefully you've watched the kind of videos to kind of show you overall what the Doppler effect is. What I want to do now is kind of get into the math of things and kind of derive the Doppler effect equations. In this video, we're going to look at just deriving the equation that shows what kind of frequency you would hear if there was a moving sound source coming towards you or away from you. What would be the frequency that you would hear in either of those situations? And we're going to try to derive that. Let's review here a little bit. If we have some kind of an object, and it's moving like to the right, it would have, or it's not moving. We'll say it's not moving to the right. So it has these waves that are coming out like this, and then there's some observer over here. They would hear a regular, just one type of pitch, one frequency, because all of these waves are spread out exactly the same. And that would be if they were on the other side too. These would be spread out exactly the same on the other side also. Okay, so now let's look at what happens if the object is like moving towards in a certain direction. So we'll take this object here, and we're going to move it to the right. And let's kind of zoom in here. Let's say, okay, here is, so it's put out a wave, and let's say the wave has got to right here. Okay, all right, and it's just about ready to put out another wave. I'm going to kind of go ahead and draw it right on the object. There's a wave that's going to be right here on the object that's just about ready to start then. Okay, so what we have here is the distance from here to here would be a wavelength, right? It'd be one wavelength. Okay. Now the key is, so we have this person over here that's going to be listening to these sounds that are coming. The key is that while this wave right here was moving over to the right, this object also was moving over to the right. So let's kind of just draw out maybe how far over this object made. And once this wave gets here, instead of this wave, starting right here, it's going to start over here somewhere because this object's moving in the meantime. Okay, so let's say that the object, gets over to, I don't know, about right there or something. Okay, so it's went over this far. Okay, and now it puts out this next wave, like right there at that point. Okay, so what you see here is that this observer over here wouldn't be hearing a wavelength from this to that. It would actually be hearing a wavelength from this to this. It would be like a shortened wavelength or a higher frequency. So when an object's moving towards a person, they hear a higher frequency than what's actually getting put out. So from here to here, that would actually be the wavelength that the observer would be hearing. We're going to do wavelength O for the observer. This is the wavelength, the effective wavelength that they would actually be hearing. Up here we have the original wavelength of what the wavelength of the sound actually is. Okay, and then what do we have right here? Well, we have here the distance that the object has actually moved. Okay, so we have a couple equations that we need to remember. The velocity of a wave is frequency times wavelength, which means the wavelength would be the velocity divided by the frequency. That's important. We also have velocity equals distance divided by time. So we have distance equals velocity times time is what we have there. Okay, so we want to figure out what is the actual frequency that this observer, which I didn't have put arms on, this observer is going to hear. So what we can do here is we can kind of start with a little equation here. We can say, hey, what would the wavelength be of the observer in comparison to all this other stuff? Well, it'd be the actual wavelength of the sound, right, minus the distance that the sound source actually traveled, right? Okay, the distance of the sound source actually traveled. All right, so what is the wavelength of the observer? Well, it'd be the wavelength of the actual sound, which of course right here is the velocity of the sound divided by the frequency of the sound. So I'm going to put in right here velocity of the sound over the frequency of the sound. Minus, it's going to be the distance that this sound source went from here to here, right? And the displacement is velocity times time. Now, this is the velocity. This v is the velocity of the actual object that's moving, not the velocity of sound. Okay, so I'm gonna actually put I'll put a vs, the velocity of the source, there, so we don't get it confused with this other v, which is the velocity of the sound. And also, it's the velocity of the source times the amount of time it took to go from here to here. Well, how much time did it take to go from there to there? Well, when it was here, it put out this original wave, right? And then when it's here, it put out the next wave. So the time from here to here is actually the time period for a wave. It's the time period between two crests. It put out a crest here, then it put out another crest here, and in between, that's the amount of time it took to go from there to there. So so I'm in for this d right here. I'm going to put in this equation right here, but I'm going to have it be it'd be the velocity of the sound source, right? Okay, times capital T. That's the period of the wave. How is the period related to the frequency? It's 1 over, right? 1 over, the period is 1 over the frequency. So this is going to be the wavelength you would actually hear would be the velocity of speed of sound divided by the frequency minus the speed of the sound source, right? Divided by the frequency also, right? Okay. So what do I have here? The wavelength of the observed wavelength would be V minus Vs over the frequency. Now, what is the wavelength you're going to hear of the observer? Well, again, I have this, right? So I could do the wavelength of the observed wavelength would be the speed of sound divided by the observed frequency. So in for this wavelength, this observed wavelength, I could put the speed of sound over the observed frequency would equal V minus Vs over the actual frequency. And I can flip this whole thing, and I have FO over the speed of sound equals F over V minus Vs, okay? And I could then multiply the V up over here, and I'm going to have the observed frequency would equal the actual frequency times a fraction of speed of sound over the speed of sound minus the speed of the actual sound source. So there is an equation, okay, that we derived. Hopefully maybe you kind of understood how we got it. You don't really need to understand that derivation, but you know I like to derive. So oops, I hope you put your seatbelt on when I did this. So this is the frequency, this FO is the frequency that you would observe. Normally we call it F prime. I'm going to change it to an F prime there. Okay, and I'll paste that little thing right there. Okay, so F prime is the frequency that you hear, and that's equal to the actual frequency of a sound times the speed of sound over the speed of sound minus how fast the object is coming towards you. Okay, and this equation here is for towards. This is coming towards you. Okay, now what happens if you're on the other side, if you're like over here, right? Okay, and you know these waves would be actually further apart, right? Okay, so really the only change there is that right here in this equation, instead of wavelength minus the d, it'd actually be wavelength plus the d. And you could do this all the way down here again. We won't do it. But you could also get a plus version. So F prime equals F times V over V plus Vs. And this would be what happens if it's going away from you. So you could use this equation if a sound source making sound is coming towards you or away from you. The only difference is the sign in the denominator. Okay, so that is talking about a sound source coming towards you or away from you. You would use these equations. In the next video, we're going to show what happens if you are running towards or away from a sound source, but the sound source is actually not moving.